Good morning, everyone. Welcome to, surprisingly, the last day of the conference. This is a very exciting session on a critically important topic for the science of consciousness, and that is the evolution of consciousness. And our first speaker is Eva Jablonka, who is an evolutionary biologist and geneticist by training. She currently is at the Institute for the History and Philosophy of Science at Tel Aviv University. Please join me in welcoming her.
Thank you. Thank you very much for inviting me, and it's a great pleasure and honor to be here. Right. Thank you. Sorry. Yes, so I'm going to talk about how we can approach the question of the evolution of consciousness. Consciousness is notoriously difficult to define, almost impossible to define, just like life. Nevertheless, I think we can have and we can develop a good evolutionary approach to the whole problem. Now, what you see here is one of the representations of what consciousness is, one way of thinking about it, as a very high-level representation. This is a calligram, a picture with the words of this poem. What is the mind? It is the sound of the breeze that passes through the pines in the Indian ink picture. So this is a third-level representation, and the picture is a fourth-level representation of this representation of representation of representation. This is a very good way of thinking, of beginning to think about it, because I think that the notion of representation, in spite of its murky history, is quite useful. Nevertheless, I'm not going to talk about this level of representation. I'm going to talk about something which we call minimal consciousness, because we want to start with the very beginning with the emergence of consciousness, with the very beginning of the evolutionary process that led to this mode of being. So, right. So, what is it? What are we talking about? As I said, I'm not going to define it. I'm just going to characterize it in a very general and intuitive way. When we're talking about subjective experiencing, we're talking about the smell of jasmine, for example, the fact that we smell, the fact that we see red, the fact that we feel joy, the fact that we feel fatigue, pain, nausea, and so on. And the big question is, why do we have this kind of thing? What is it? Why is there such subjective experiencing and not merely the ability to respond to stimuli, acting without feeling? And a related question is, what is it exactly that we're talking about? Are we talking about a trait of an organism? Are we talking about a process? Or are we talking about a mode of being? Like, you can be inanimate, you can be animate, you can be sentient, you can be rational. Are we talking about these things? The way that we choose to think about it, the way that we find most fruitful, is to think about consciousness as a mode of being. And following Aristotle, we suggest that subjective experiencing, like life, is an unmettered, actively and teleologically organized mode of being. A specific type of mode of being. So is life, so is rationality, and so is also sentience. So, right, I will start with something that to explain why we choose an evolutionary approach. Here's a citation from Richard Feynman on his blackboard at the time of his death. What I cannot create, I do not understand. Very well-known quotation, used in many contexts. And I think that there is something that we do understand the things we build. Now, nobody as yet built a conscious robot. People try, and people will probably one day succeed, but this is not yet, hasn't happened. What did happen was that through the evolutionary process, the creatures, which we call conscious, have come into being. And the evolutionary process is something that we can think about. We have the tools of thinking about it. We know how to think about it. And we can try and follow the way in which consciousness appeared and evolved in the living world. So, how do we do it? There are different ways of of using the evolutionary approach. And what we are doing, we are using what is called the evolutionary transition approach. That is, we're trying to understand how, from creatures that we would not characterize as conscious, we evolved creatures which we do characterize as conscious. As I say, I'm not going to argue here whether consciousness is a basic kind of stuff in the universe or something that a primitive of the universe or not. I'm talking about the common sense feeling that we have about consciousness as I described it, the ability to feel all kinds of things, to have subjective experiencing, to perceive rather than just to process sensory information. So we suggest an evolutionary transition approach to the study of consciousness, and it is inspired by the work of a Hungarian theoretical chemist called Tibor Ganti, which was further developed by Maynard Smith and Satmary in their book, The Major Transitions in Evolution. And this kind of approach starts with characterizing the subject of the study. So let's say that you want to study the origin of life. What you do first is you list the characteristics about which there is a very general consensus that these are the characteristics of life. Okay, people may argue whether this characteristic is more important. That characteristic, is metabolism more important than replication? Is having a boundary more important than something like reproduction? These are all very, very good arguments and very important for the advancement of this science. But basically, there is a list of things that people more or less agree. These are the characteristics of life, so that if we go to another planet and find something with this characteristic, we will say, well, we have a good reason for thinking that this is either alive or has been made by living organisms. Okay, so this is the first thing. The second is we want to identify, excuse me, this has got stuck, identify a capacity of the system that entails these characteristics. Such a capacity enables us, if we find a particular structure that indicates a particular capacity, and this capacity is such that we can reverse engineer from this capacity the system that enables this capacity to exist. And this system have all the characteristics of the list. We say, well, this is a good marker, good evolutionary marker for the mode of being in which we are interested. And then, once we have this, we can also try to create some kind of model of the system. This is what Ganti did with life. And we took this approach, and we thought he didn't do it exactly in this order. I will not go into it, but this is the basic approach, and we took this approach, and we said, let's apply it to consciousness, because consciousness, like life, defies definition. Like life, it is a mode of being with its own specific values. Like life, it gives rise to new types of autopoietic principles. In the case of life, it is what we call functions. In the case of sentience, it is what we call mental representations. In the case of rationality, it is what we call symbolic, cultural concepts. In each case, this is what happens with the mode of being. So, okay, we can start to think about it in this way and start perhaps to create some model or a model of the capacity that will enable us to think more rigorously about this question. Okay, so here is what would happen if we arrived to some kind of planet and found a big molecule, such as DNA molecule, on it. We don't find anything else, just these molecules. Now, we find these molecules and we ask ourselves, well, what does it mean? I mean, obviously, these molecules could not have been created spontaneously. We know everything about the geology of the place. We know a lot about biology, about chemistry, about a lot of sciences. But this is the only thing that we find. And then we try to say, okay, for this kind of polymer to exist, and this polymer seems to us like it can lead to some kind of heredity. It can be, for example, through replication, it can be something that we can call hereditary material. If we have this kind of, if we find this kind of thing, and we reverse engineering the enabling system in which this kind of thing was synthesized, could have been synthesized, which could give rise to such a thing, because, as I say, it cannot be formed spontaneously, then by reverse engineering, we come to something like a protocell. And it is the protocell, of course, that is alive. It is not the polymer that is alive. It is the protocell with the polymer which shows sustainable life. If this polymer is long enough, and it enables us to have what we call unlimited heredity. Unlimited heredity means not unlimited in the mathematical sense, it means unlimited in the sense that there is a huge number of different variants which can be selected, much, much, much greater than the possible environments that the entity, that the system can ever meet. So, okay. So what is the capacity? But first, before we go to the capacity, we have looked at, me and Simona Ginsburg, with whom I did the work. And we looked at various things that have been said, various characteristics of life, that different people from philosophy of mind, from neuroscience, from cognitive sciences, have enumerated as characterizing something that we will call, in this case, conscious. Sentient. So people say in order for something to be called a sentient creature, the way that it perceives the world has to have both unity and diversity. There must be global availability of information. The system must have a very flexible value system so that it can assign value of good and bad and all the kind of variations in between to different states. It has to have temporal thickness. The experience has to have some kind of temporal depth, something that James talked about, the phenomenologists talked about quite a lot. There must be a huge amount of adaptive plasticity and a lot of processes of selection and exclusion within the system. The intentionality is very important, intentionality in the sense, of course, of aboutness, and in the simple way that we think about it, it is some kind of mapping representation of the world body and their relations. So there must be models of the world, of the body, of the relation between them within the system. And we're talking about embodiment, agency, and self, which all these things are, of course, semi-overlapping. And it is a good thing that they are, because they form a system. So we need to have embodiment, need to have agency, and we need to have something that we can call a self. And there is coherence, which entail coherence and flexible stability of the world and the body images from a point of view. We found that a lot of people from very different disciplines, each of them has a favorite among this list. But never mind the favorite, more or less a lot of people will agree on this list, and some people will maybe suggest some other things, additional things. Some people will say, look, this property can be subtracted because other properties sort of fulfill all the conditions it describes, but we think that this is a reasonable list, and it conforms to a lot of stuff that we found in the literature. So we said, okay, so Minot, Smith, and Satmary, following Ganti, suggested that unlimited heredity, the capacity for unlimited heredity, is a good evolutionary marker of life. And we think this is a brilliant idea. It's a very, very good tool for thought. So we were thinking, and we spent a year trying to figure out what can be a good transition marker for consciousness, for basic consciousness. I'm all the time talking about the very minimal consciousness, not about reflective consciousness. So after a lot of thinking at different levels, from the molecular through the anatomical to the behavioral, we decided that we were satisfied with our own suggestion that a particular mode of learning, which we call unlimited associative learning, UAL, is a good transition marker for sentience. And the reason is that when we reverse engineer from a system that can satisfy this type of learning, if we reverse engineer from it, we will go back to a system that has all the 7 characteristics that I showed you in the last slide. So what is this unlimited associative learning? In what way is it different from limited associative learning, or from non-limited associative, or from non-associative learning? So the first thing is that the conditional stimulus, the CS, or the behavior that the animal shows, that the entity shows, is compound. It consists of several fused features, so that when we see, for example, a cat, we see the cat, we see its shape, we see its color, if we have color vision, and we see its movement all at the same time. And we see these features as a conjunction. We don't just add them together. We see them together as a whole. The second thing is that the CS that we encounter is novel. It has never been learned before, nor has it been, nor is it the result of evolution that led to a reflex eliciting kind of response to this particular stimulus. And the third is that on the basis of this CS, we can build another form of learning so that this CS can become a US, an unconditional stimulus. So we can have a second-order learning, sometimes even third-order learning. We don't go very much higher than that, even in humans. Sometimes we do. Okay, and this is just one example, a rather complicated example. We don't need that much complication, but this is intuitively understandable. This is an example of unlimited associative learning, spatial learning, where the little mouse down there has to learn the arena, this new arena in which it is. It has to learn it bit by bit, gradually, and it has to realize that there are paths which are dangerous, there are paths which are rewarding, and so on. And it will, we know that in such cases, it will need to represent this. It will have to have something like a cognitive map. Okay. So if we're thinking about unlimited associative learning, and we're thinking about what it gives an organism that have this, UAL is extremely generative, right? Because we can have a lot of different combinations of stimuli can be joined together to form a percept, a lot, a huge number. The same is true about a combination of actions. A lot of combinations of actions can be discriminated and can lead to behaviors. Although the elements, the components of the particular actions or the components of a particular percept can be the same, what is really important here is not just which are the components, but how are they organized together? What kind of whole are they creating? And the differences between different wholes, between different compounds, is the hallmark of this mode of learning, of unlimited associative learning, and it is a highly generative system. The other thing is that it is a recursive system, because, as I said, a CS can become a US, and then this can become, in turn, another US. So there is a kind of recursion there. There is a recursive process of representation. And just, we say, as unlimited heredity enabled open-ended evolution, because only when you have unlimited heredity, a lot of possible variations, again, unlimited, not in the mathematical sense, but in the ecological sense, a lot more than the organism is likely to encounter, it led to open-ended evolution. So unlimited associative learning allowed open-ended ontogenetic adjustments, and through cumulative learning, can lead to very complex behaviors. And we're talking here about a mode of learning that is not only that, of course, we display as humans, but not only us. As I will show you, many other animals seem to display it, definitely not all. Okay, this is intuitively maybe satisfying, but we have not shown yet that this kind of the features of unlimited associative learning, when we reverse engineer from such a capacity, really lead to the list of properties about which there is a general consensus that they are more or less characterizing sentience, in the sense that when we arrive, again, to another planet and we find a mode of being with this characteristic, we will say, well, this is sentient, or it has been built by very clever engineers who know a lot about sentience and put it in there, right? Okay. So, before we do that, before I will argue that we can do this reverse engineering and it does lead to this list, I want to describe very generally and in a very simple way the functional architecture of of unlimited associative learning. So, in order for this type of behavior to exist, there must be mechanisms that integrate various underlying features to form a compound. And the encoding must be multi-stage, hierarchical, and predictive, based on discrepancy signals, because this is the only way that something that complex can be ever formed, according to our understanding of the matter. I know that there are a lot of ways of doing predictive coding. I'm not going to go into it, but something like that is necessary. And hierarchical kind of processing is necessary. Then we need, there should be an interaction. There must be the formation within the system of something that we call a self model, a world model, and the model of prospective action. So the system can be built in such a way that these models can be said to exist in it. And there must be an interaction between these models. So there must be something like a model of models. And there must be a dedicated memory system that enables subsequent retrieval based on the temporal compound patterns. So you don't only remember the bits of an experience, you can sometimes remember a combination of bits of the experience, not necessarily all of it, because there is the phenomenon of completion, but not just one element, because one element can lead to endless possibilities because of the endless combinations in which this element exists. Oh my God. Okay, so this is the model. So this is a toy model, not of consciousness, I want to stress. It is a toy model of unlimited associative learning. And the important thing that we see with the different colors, the blue colors are the sensory elements. So there is sensory integration, and the sensory integration includes exteroception, interoception, and proprioception. The yellow things are the motor elements, and what we have here are the MIU, the motor integrating unit, is where the model of prospective action is formed. The AU is where all these things, all these models of the world, on the one hand, on the blue, and the model of action, on the other hand, the yellow, join together. And there is also, since we are describing learning, there's also reinforcement. If I had time, I would tell you in detail what time 1, time 2, time 3 mean here, how these things are correlated in time. And we need to have a system of memory, the green thing, where there is where compound features of the world and of action are stored, so they can be retrieved. And these things are connected. You see, usually there are two arrows, and the arrow that comes from the top is something that we can call a kind of generative model, if we talk in the language of Carl Friston. And the arrows that go from the bottom up are prediction errors. And then there is another prediction error in the behaviorist term, in the behavior-related term, that goes from the integrating unit down and leads to action, to the action that we actually see. Now, if we reverse engineer, what we see here is that in order for this model to exist, we need to have sensory motor binding. We have to have accessibility so that the different systems interact. We have to have systemic evaluation system. This is the red bit thing. We have to have memory. We have to have a kind of selection and memory. I didn't show you much selection here. There's only one thing, and this is the something that is the EC here, you see. This is the efferent copy. This is what leads the animal to assign different value and lead to different behavior once the same sensory and discriminate between sensory stimuli that are the result of its own action and the same sensory stimuli that are the result of something which is independent of actions that comes from the world. It is very, very important for the construction of self. There are a lot of exclusion processes in this system, which I have not shown here, but we describe in detail, more or less detail, in our very big book that describes this set of ideas. Now, we can show that the attributes of UAL entail the consciousness characteristics. If we go through the consciousness characteristics one by one, which I cannot do at the moment, but if we would go through them, we would see that each of these characteristics is entailed by this architecture. And that is why we say this is a good model. This is a good evolutionary marker. We're not saying it is the best that can ever be found. If you find something better, we will be very happy. But it is the best that we could find, and it's something we could work with. The reason we could work with it is that we can follow the evolution of unlimited associative learning, the marker. We can see how it emerged, in what context it emerged, and so on, whereas we cannot really follow very well the evolution of consciousness, because it is a very slippery concept. So we choose a cognitive capacity, who is a good marker, and we work with this. Now, the interesting thing is, when we are looking who has UAL in the animal world, we find three groups. Most vertebrates, not all, but most vertebrates, some arthropods, and some mollusks. The mollusks are the cephalopods, the arthropods, there are several groups, and the vertebrates are all vertebrates except the very, very, very primitive fish-like creatures at the very bottom, at the very basal part of the vertebrate tree. And when we're looking at, when did these things appear in evolution, so now we know what we're looking at. So we also know what brain areas will instantiate this. Before we had this marker, we didn't know what to look at in the brain, so now we know, and when we look at brains of animals, and we know a lot more about brains than about behavior and consciousness, when we look at the brains of animals that live today, and extant animals, and fossils of animals, we can say, and we can infer that this capacity for UAL, and therefore for consciousness, appeared during the Cambrian. So here are the brain areas. Here are brains. I mean, this brain belongs to this kind of creatures. This brain belongs to the arthropods. This is the brain. This is the brain of a cephalopod. And this is an interesting thing showing us that the same functional architecture is found in the mammalian brain and the insect brain. It's just unbelievably amazing to see how close the functional parallel is. The structures are totally different. Okay, and this is the Cambrian. Here you see all the creatures of the Cambrian. Most of them arthropods. There are two little fish there, and also other creatures. But these are the creatures, many of which we think had elementary, minimal consciousness. And there are all kinds of conclusions that we can draw. But I think that the talk has given you most of the conclusions, and we can discuss them at greater length in the discussion. Thank you very much.
Thank you very much. It's my great pleasure now to welcome up Professor Nicholas Humphrey from the University of Cambridge. Panpsychists beware. We're going to hear about the limits of sentience.
Good, it's there at last. Sorry about that delay. It's wonderful to be in such a diverse meeting. and I have similar titles to our talks, but I think my talk could not be more different from hers. I tremendously admire her approach to things, but it's rather different from the kind of way I'm going to discuss issues this morning. I'm going to be talking about sentience at a much higher level, about phenomenal consciousness. I want to know what sentience is, what phenomenal consciousness is, and where it is. Just for who else besides ourselves is it like something to see red or to feel pain? And I'm not sure at all that that's implied by anything which Eva has talked about yet. I know there are many other meanings of consciousness, and they've been flying around this meeting, but this is the one which I think we can all agree in the end is the one we care about, phenomenal consciousness. It's that which really matters. Now, most of us, I think, believe that this sentience club, phenomenal consciousness club, does extend to many other animals, even if no animal makes such a deal of it as we ourselves do. Some of us think that all living things are sentient. Some of us think that intelligent machines will one day be sentient. Some think that phenomenal consciousness is a basic property of organized matter, so that matter matters to itself. Well, whatever answers we come to, we want to know the answers for two reasons. One is simply to fill in the picture of the world around us. It's intellectually provoking not to know the facts about what lies beneath the surface of other creatures' lives. As explorers, we want to lift the veil. But the other reason is a weightier one. We want to know who or what else is sentient so as to know where our moral obligations lie. What relevance do we have to the lives of others? In whatever world we live, what ethical footprint do we live? Well, I've just 20 minutes, and I'm going to use this time simply to outline a very bare theory of sentience that I hope can help at least to guide the discussion of those bigger issues. But we have to start by narrowing the possibilities. So I'm going to start by assuming that sentience is not present everywhere. I'm not a panpsychist, and in fact I can't make sense of that position. I'll assume it is in fact a biological phenomenon. When and where it exists, it's a feature of animal minds. Maybe I should include plant minds, at least in principle. And this means it's almost certainly an evolutionary adaptation. It's been shaped by natural selection. So I'll take humans as the starting point, and I want to discuss what sentience is and how it works in us. I think it's best to start at the top rather than at the bottom, as Eva did in her talk. I want to point to the benefits that phenomenal consciousness brings us, and then ask whether those might explain why it's been selected in our ancestors. And if we have answers to the what and the why of sentience for humans, we'll hopefully be in a better position to make informed guesses about who else. But be warned, the story I'm going to tell is not a simple one. I'm not going to pluck a statistic out of the air, such as integrated information, and say, problem solved. Well, first, some definitions. I'm not going to make too much of a meal of this, but we need something. I take it that what we mean by sentience is the faculty of experiencing sensations with phenomenal properties. That's to say, for a sentient creature, it's like something to have sensations, to interact with sensory stimuli arriving at the body's surface. It's like something to have your hair pulled, or to roast your nose in front of a fire, or to run through the cold, salt waves. Sensation, let's be clear, is not the same thing as perception. Perception is the way you represent the external world, the waves as such, the fire as such. But sensation is something much more personal. It's the way you represent what's happening to you and how you, as a subject, evaluate it. The pain is in your toe, and it's horrible. The sweet taste is on your tongue, and it's sickly. The red light is before your eyes, and it's stirring you up. It's as if in having sensations, you're both registering the objective fact of stimulation and expressing your personal bodily opinion about it. And indeed, as we'll see shortly, I think you are doing just that. But it's the way you do it that's so surprising. What you represent the bodily opinion as. Where do these extra qualitative dimensions come from? What can make the subjective present created by sensations seem so rich and deep, as if you are living in thick time? What can Kandinsky mean when he writes, "Color is the power which directly influences the soul. Color is the keyboard, the eyes are the hammers, the soul is the piano with many strings"? Well, prompted by Kandinsky, I'd like to propose a rather grand analogy. When you're the subject of sensations, it's as if you're sitting at the console of a cinema organ, creating a line of music to express your experience of what's happening before your eyes. The themes for the organist are highly practiced, so you don't have to think about the picture and what to play in response. You just find yourself doing it. Your performance follows what's happening on screen, but it doesn't merely track the picture. It adds a personal dimension and colors it with emotion. And on top of all, it does add a mysterious dimension of harmony and temporal depth. But now let's ask what it's like for you, the organist, to be there in that position. You're watching the screen and you're making something of it with your body. What could you discover about the movie and how you feel about it by attending to your own performance? Well, crucially, you have two sources of information. One, you are playing the keyboard and you can follow your own actions. You have immediate access to what you are doing. And then, secondly, you can listen to the sound of the music that you're making. So you can learn about your own reactions at one remove. And on this level, I believe the analogy captures a crucial feature of phenomenal experience, the duality of access to what it's like. In the words of the poet Ossip Mandelstam, you are the gardener and also the flower. I'll come back to that. Okay, but this, of course, is just an analogy. So let's ask about what is the reality and how it evolved. I'll outline the theory I've developed over a good many years now. My starting point is that sensations are indeed an active response to sensory stimulation. They're something the subject is doing. They are, or at least they once were, a form of bodily expression, an affect-laden response to stimuli arriving at the body's surface. Imagine a primitive animal floating in the primeval organ. Things are happening to it. Chemicals wash up against it. Pressure waves bump it. Light falls on it. These things matter to it. And so, for example, it responds to the light by turning away. It doesn't like the light. Perhaps it's pleased by the chemical stimulations there, and perhaps it's more relaxed about the pressure waves. These responses are reflex behaviors. They're wriggles of rejection or acceptance, I've called them in the past. They've been shaped by natural selection so as to be adaptive. They enact what the stimulation means to the animal, but to begin with, of course, the animal is in no way mentally aware of what's going on. However, as these creatures evolve, there does come a point when they would stand to benefit from having a mental representation of the stimulus. What's going on here? And as it happens, there's a neat way of doing this. The animal has simply to monitor its own response. The response may be purely reflex, but it potentially carries loads of information about the external stimulus, what kind of stimulus it is, where it's occurring, and especially what import it has for the animal's well-being. So the animal can represent what the stimulation means by the simple trick of copying its own motor command signals, by making perhaps what others people call an efference copy of the signals it's sending to make the response. The response enacts the meaning, the command signals create the response, thus the efference copy directly captures the meaning. Now, if this is how it's done, and I'm pretty certain of it, then sensation, let's now call it that, originates as a kind of unmediated feeling by doing. But of course, things were never going to stay like that. As these creatures evolved further and developed more sophisticated behavior, there's bound to come a point when the original bodily responses are no longer appropriate. The animal no longer wants to recoil reflexly from light, say, and yet it does still want to know that light is falling on its body and that it doesn't like it. Then what to do? The answer natural selection hits on is ingenious. It is for the reflex responses to become internalized, or as I've put it, privatized. Let's stop working. So they no longer now result in actual bodily behavior, but there is still an efference copy that can be read to represent what's happening. Okay, so let's fast forward to where we are today, to where we humans are. The upshot is that when you experience sensory stimulation, you're still responding with the ancient action pattern handed down from your ancestors. But my thing's not working now. And you can still read it, but now it's become a virtual expression occurring at the level of a virtual body inside your own head. So let's take the case of seeing red, for example. Red light arrives at your eyes, and next thing, behind the scenes, you make a virtual affective response to it. Here it is. It's an ongoing response, and I'll call it redding. And now, where's your sensation in all of this? The sensation is still your reading of a copy of your own response. To have the sensation of red is to find yourself redding. So to take stock, I hope you've noticed how this story is converging with the analogy I offered earlier. You're seated at the organ, matching your responses to the stream of stimulation, pumping out a stream of motor commands that express what you feel and following what's happening via the efference copy. Except, of course, you're checking on your own performance, but of course there is something rather major missing. You may be having a sensation, but it's a pretty thin one. Where's the music? Where's the beef? It's obvious that the evolution of sensory experience can't have rested here. There has to be another chapter to the story, a chapter that tells of some dramatic development that fills out sensations and adds the phenomenal richness we humans prize so highly. Well, I believe the key to this lies with the process of privatization that I've just described. Back at the beginning, in primitive animals, the responses to sensory stimuli took place at the site of stimulation on the body's surface. Once privatized, however, the responses now ended within the brain. And this had a remarkable, even if it was fortuitous, a remarkable result. It meant that a feedback loop was created between the motor and sensory regions of the brain, a loop with the capacity to sustain recursive activity, going round and round, catching its own tail. And this was potentially game-changing. Crucially, it meant that the activity could be drawn out in time so as to create the thick moment of sensory consciousness. But more than this, it meant that the activity could be channeled and stabilized into a remarkable mathematical object. Suppose that each time the activity circles around this circuit, the transmission from input to output, the characteristics of that is altered by the activity the previous time around. Then the development activity in this circuit is going to be described by a delay differential equation. And typically, this means it will either develop chaotically, or else it will settle into a complex attractor state. This film clip shows an example of just such a complex pattern developing in a feedback loop, a simple feedback loop. Now, this attractor exists in just 3 dimensions, but often the attractor will turn out to be very much more complicated with remarkable hyperdimensional properties. So think now what this could mean for the evolution of sensations. With all those extra dimensions to play with, the way was open for natural selection to radically transform the properties of the looping sensory responses, and thus the properties of the sensations that copy them. Sensations could be lifted into the realm of hyperreality, becoming ethereal objects worth contemplating as phenomena in their own right. And I think that's just what happened. So back to the organist inside your head. Your reading, you'll see, has now undergone a remarkable uplift. Now there's wind in the bellow of the organ. We can do better than plain red light. Let's jazz it up a bit. Now, I'll remind you, you still have immediate access to your performance through the efference copy of what you're doing. But now, in addition, you can inspect and introspect the surreal work of art that you're creating. And I want to stress again the significance of this dual access. I think it does much to explain why theorists are so often at cross purposes about the status of phenomenal consciousness. Are the phenomenal properties real, or are they an illusion? Are they intrinsic, or are they derived? Are they immediate, or are they secondary? When you are both the gardener and the flower, the answer can be both. So this is where we've arrived. This is what makes it what it's like for us to have sensations, us humans. But we've arrived there by stages, and presumably every stage must have brought some distinct benefit to biological survival. So just why did evolution take this course? It's easy to explain the earliest stage where our primitive ancestors took advantage of an efference copy to represent the meaning of bodily stimulation. Obviously, it's a good idea to have sensations that carry information about what's happening to you and how it affects you. It's the second stage, where sensations took off to become elaborated, phenomenal sensations that's much more of a challenge to explain. Well, I suggest we look again at that first stage. We've already remarked that this particular way of representing things was never a neutral, objective one. Your sensations represent what the stimulation means to you, how you feel, and they do this by taking account of what you're doing using an efference copy, which, as Eva remarked, is basic to the very nature of understanding oneself. So the fact is that sensations have always been as much about being you as about the external stimulation. It would seem then that from the beginning, sensations might have been pre-adapted to play a rather special, rather grander role. They were ripe to be co-opted to lay the foundations of the self. The philosopher David Hume famously concluded that he himself was indeed nothing else than a bundle of sensations. For my part, when I enter most intimately into what I call myself, I always stumble on some particular sensation or other, of heat or cold, light or shade, love or hatred, pain or pleasure. When my sensations are removed for any time, as by sound sleep, I may truly be said not to exist. But Hume has a bit of a problem with this. He worries that this sensation-based self is nothing to be proud of. He thinks it lacks substance. He likens sensory experience to a theatre with a constantly shifting display of sensations that successively make their appearance, pass, repass, glide away, and mingle in an infinite variety of postures and situations. And he goes on, there is properly no simplicity in it at one time, no identity indifferent, nor have we the most distant notion of the place where these scenes are represented or of the materials of which it's composed. How then, he asks, can sensations underpin the self with a big S, the I, the thread that runs through our mental lives? Well, is this going to mean that this role for sensations is a non-starter? I don't think so. I'm not saying that Hume's worry is groundless. I'd agree that if sensations had remained unelaborated and voiceless, as they presumably have done in relatively primitive creatures, he would be right to question whether they're up to the job of supporting a robust sense of self. But surely that's precisely why natural selection might have moved in to reinvent sensations, giving them the added oomph that lifts them into the sphere of phenomenal significance. The fact is, Hume is seriously underestimating sensations as we human beings experience them. He says we don't have a notion of where our experience is located or what it's materially made of, but he's wrong. We do have a notion. Actually, we each have first-hand evidence that sensations are out of this world. The where of phenomenal experience is nowhere, and the materials are immaterial. That's the wonder of it. Sensations give us the feeling that there is an essential, non-physical dimension to our lives. They fix our sense of self as a bubble of spiritual substance floating above a world of things. And now we see why natural selection would have done this. Because for humans at least, a self of this kind is hugely adaptive. It gives us something substantive to hold on to, something to aim for, a ball to keep in the air. It provides us with a remarkable imperative to invest in our own future. It becomes a focus of our hopes and desires and in the future of others like ourselves. For humans, the experience of phenomenal consciousness is what makes us conceive of ourselves and others like us as significant individuals. Every one of us becomes a person, an independent, private, responsible, free-willed locus of conscious being. Consciousness imbues the self with metaphysical significance and so changes the value we place on our own and other lives. Now, how far do we share this conception of the self and this ambition for self-advancement with other non-human creatures? Who here is an insider to consciousness as we are? Well, that's the question, and it's a question that perhaps wisely I've left myself almost no time to answer. I said at the start that if we have answers to the what and the why of sentience for humans, we'll be in a better position to make informed guesses about who else has it. Well, very briefly, where has this discussion got us to? First, as to the what. Phenomenal consciousness, as we've seen, is anything but simple. Philosophers sometimes talk of conscious sensations as raw feels, the redness of red, the paininess of pain. But the reality is that sensations as we experience them are very far from raw. They are thoroughly cooked. They are the culmination of a remarkable evolutionary trajectory. Arguably, sentience is the jewel in the crown of brain and cognitive evolution. So when it comes to asking who, I think we can rule out on purely structural grounds any creature that hasn't got the right kind of brain and the right kind of history. The right kind of brain means, at the very least, a brain capable of housing the intricate circuitry required to generate attractor states with higher-order phenomenal properties, to represent them in a double way, and what's more, to be inspired by the experience. And I'd say this means that phenomenal consciousness can only exist in large-brained, intelligent animals. Dogs, elephants, octopuses maybe, lobsters, snails, butterflies, not a chance. But of course, the right kind of brain with the right kind of history means much more than this. It means a brain that not only has the structural potential to deliver phenomenal consciousness, but has been designed to actually deliver it. And since this design can only have arisen through selection, this in turn means a brain whose owner can reap the survival benefits of having a phenomenally conscious self. So this is the why of sentience, and I think this imposes much tighter constraints on the who. It means we can further rule out any creature whose behavioral ecology and lifestyle would make having this grand sense of self superfluous. In modern humans, the conscious self proves its worth in the context of a social system that emphasizes individualism and autonomy and is supported by a rich language-based culture. We can be sure that no non-human animal is capable of making such a big deal of the self as humans do. If non-human animals have souls, well, they certainly don't know they've got them, and that's what counts. This could mean that sentience as we know it is a very recent innovation. It could even mean that humans are the only sentient, phenomenally conscious creatures on Earth. But I don't think we need take quite such a radical line. There are several non-human species for which there's behavioral evidence of self-consciousness and individualism. Elephants, dogs, crows, they all show at least glimmers of personhood. But now I'd rule out octopuses. I know of no reason to believe that octopuses conceive of themselves as persons or as anything like that. The bottom line is that phenomenal consciousness would be wasted in most creatures, even those with brains that are large enough to house it. Suppose we could, in fact, genetically engineer an octopus to have phenomenal consciousness. I believe the new genes would not be maintained by selection because the newfound selfhood would make little or no difference to the octopus's survival in its relatively asocial and independent world. But hey, we're in Switzerland, so we're in the home of the cuckoo clock. So let me end with another contrived analogy. I hope no one will take offense. Here's a French watch that represents the time in two ways. And here's a Swiss clock that does the same. Who's going to buy the Swiss clock and keep on winding it up? Well, of course, the answer is only the highly advanced, spiritually superior people who live here, love their clocks, and find the extravagant display a cause for national pride. So no wonder the Swiss leave the French standing. Thank you.
Thank you very much. And now on to our last speaker. There's a change in the program, but it's a great privilege for us to welcome up Dr. David Edelman, who is now a visiting professor at Dartmouth, and who is going to discuss distance vision and the origins of consciousness. Dr. Edelman.
Thank you very much, and good morning. Given the distinguished company I am following today and the depth and variegated insightfulness of their expositions, I feel like a pygmy standing on the shoulders of giants, to bastardize a quote. But I will persist and try to make a case today for the idea that some form of primary consciousness, as we might understand it, was quite dependent on the emergence of a particular kind of a sense, vision, but not just plain vanilla vision, distance vision, the ability to see objects from afar and to accommodate to see objects close by. But the distance aspect of that is the most important attribute, and I will get into why I believe that's the case shortly. All right, so the Cambrian, I'm going to start where Ava sort of started. So, but I will sort of breeze through this because I think she covered a lot of that fruitful ground already. You can think of the Cambrian as a kind of a golden age of sensation and movement, because in fact, it is a period of time in which we see a lot of the major sensory structures, sensory apparatuses, sensation, sort of emerging in a sort of an efflorescent way. Eyes are invented and reinvented perhaps a half dozen or more times, more or less independently in different phyla. And I don't want to imply that there wasn't complexity in life before this. We do have some evidence, spotty as it is, that the Ediacaran was a sort of a rich period as well. But the Cambrian explosion really distinguishes itself. This is just a molecular time tree of invertebrate radiations. Don't give it too much mind, except to notice that it's quite elaborate. And this really sort of exposes the explosive nature of the Cambrian and just how much sort of came about at that time. On the left-hand side, you see a variety of different complex life forms, some of which, at least all of these, in fact, have some form of vision. We really don't, we can't say they have distant vision. They probably don't, because in the case of these particular animals, their vision would be more like very primitive insect vision. And we do have evidence for that in the fossil record. So here is another variation of what you just saw, only with a picture of the very first sort of known exposure of the Cambrian explosion. This is the Burgess Shale. This picture was actually assembled as a panorama by Charles Walcott, who's very much associated with the discovery of the Burgess Shale. All right, so let's start in a very simple sort of way, in a sort of in the realm of physics, the nature of light and what an organism that develops vision is actually dealing with. So in the case of light, animals with vision over time have developed a way to distinguish or to differentiate different aspects of light, in this case, wavelength, different wavelengths, and the subproperties of wavelength, reflection, transmission, absorption, scattering, physical properties, other than brighter or dimmer, there are spectral properties of light that yield these differential wavelengths, and the nervous systems of animals, probably very early on, were able to discriminate this, and this was a matter of survival, in fact. Polarization is another property. We're not terribly familiar with this. We don't have really firsthand knowledge of this because we really don't have polarizing vision. But many animals, in fact, do, from certain birds, many birds, in fact, to a lot of marine invertebrates. So Cambrian ecology, there's sort of a seminal change that we believe occurred during the Cambrian, where life had to eventually encountered topology or topography that was transitioning from two-dimensional, that is, low-lying sort of mats of flora, at the bottom of the ancient seas, to something that was more sort of three-dimensional. And eventually, animals started to move. They started very much as sessile sorts of organisms. They were tethered to the bottom of the ocean, but eventually they developed movement, and that happened probably in a period of less than 10 million years. Mobility at depths at which these animals could sort of perceive photic distinctions. And this is very shallow. This is less than 50 feet. Those animals that were able to make those kinds of discriminations were able to exploit a variety of food sources, many of them more far-flung. They didn't simply rely on food drifting by and catching the food anymore. They could actively search for the food and eventually, and inevitably, hunt for the food and engaged in predatory strategies. And there was sort of an arms race of innovation, and we can extrapolate this not from, we don't have any obvious material record of behavior, but we can extrapolate this from structure, from what we see in the fossils, that faster locomotion was developing, armor was developing, mimicry of a certain form whereby animals could mimic certain neuropeptides or neuromodulatory signals to throw other animals off, and then finally refinements in vision. So these are some early experiments in vision during the Cambrian. The creature on the top left is Pikaia. It's, as you can see, basically sightless. You see other Cambrian creatures that are developing eyes. And then you see this real oddity, this animal that sort of defies what we consider sort of modern embryology in a certain sense, because it has bilateral symmetry through much of its body, but it has a singular eye. It's a cyclops. It has one eye, one rather large, formidable, compound eye, Cambropachycope. All right. So I've talked about eyes evolving a number of times. So they sort of represent the epitome of convergent evolution. They're developing in more or less otherwise independent animals whose common ancestor was eyeless. So they're not developing monophyletically as eyed creatures from a single-eyed ancestor. In fact, they seem to have developed eyes independently, and this happened many times. But at a far deeper level, of course, there's homology. There's what you might call, to borrow a phrase from Neil Shubin and Clifford Tabin, deep homology, only I'm not talking per se about genetics here. I'm talking about a sort of a higher level of organization. I'm talking about proteins. In this case, photoreceptors, and specifically rhabdomeric photoreceptors, opsin as an early photopigment. So these were very conserved, and these building blocks were used many times in the emergence of eyes in these different creatures. All right, so eyes evolved many times, but there's a certain aspect of spatial acuity at distance that seems to have been rather unusual early on. Not so unusual anymore, of course, and I believe very important. I hope to persuade you of that today. So we know that light sensing is quite ancient. It probably, in fact, it may very well precede the Cambrian, although we're not absolutely positive of that. And you can distinguish that, a simple light sensing organ with a series of cells, perhaps pigmented cells, but maybe not, cells that are photosensors lying on a flat surface on the skin. You can distinguish that from a simple eye, where in fact, there's sort of a limited capacity to define, basically to array photons in sort of a spatial organization. And that comes from a combination of photoreceptors arranged or embedded within within some other cells that sort of parse them from their neighbors, and enabling sort of the representation, a very primitive sort of spatial representation, but very, very primitive. Okay, and eventually, the great variety of eyes that all appear, again, within a very short time after probably about 540 million years, in the depth of the Cambrian explosion. And essentially, all of the modern forms of eyes that we know today appeared during the Cambrian in all of their varieties. And many different sort of subflavors, but two basic flavors that are sort of represented up here. So on the top, you have a jumping spider that has, it has 8 eyes, but only 2 of those eyes are capable of resolving objects. And in fact, interestingly enough, at least some jumping spiders are able to perceive objects at great distance. They actually have distance vision, even though it works quite differently than vertebrate distance vision. Versus the mantis shrimp, which is a typical animal with compound eyes. It's an animal that has compound eyes very much like an insect, but it's not. And so here are all the sort of leitmotifs of these different eyes, but these are the 2 basic flavors. Compound eyes, essentially fixed in terms of the light they're bringing in, no real capacity to focus per se, versus single compartment eyes. I put the jumping spider up here, but of course we belong to this group, even though our eyes look quite different morphologically than spider eyes. So let's start from early on, because I'm making an evolutionary case, and I'm going to give you sort of the building blocks to understand how first we construct these sorts of organs and then the brains underlying them. Leading up to that sort of lacuna where we find ourselves in trying to make the jump between sort of complex structures, sensory motor and central nervous structures, and conscious awareness, this thing that's seemingly immaterial from the material. So well before awareness, I believe there were nervous systems, but how do we get from simple cells to complex nervous systems? So I'm not going to dwell on this too long, but I'm going to go over really rather quickly a laundry list of the various stages. And we can really reconstruct these stages quite well by now, given what we know about modern living organisms, in combination with what we now know of the fossil record, as limited as that is. Okay, so we know that early on, cell membranes eventually develop. They separate internal and external environments. There's sort of a self-regulation that necessarily has to happen. Flow of ions across membranes that regulate internal state versus the great big bad outside world. So a form of homeostasis happens rather early. Organelles that engage in cellular housekeeping. They're symbionts. They could be mitochondria in the case of animals. They could be chloroplasts in the case of plants. Nevertheless, they engage in housekeeping, but they actually do something that's rather revolutionary. They provide an internal energy source for animals within whom cellular structures that are composed of many cells, are deeply buried, that can't rely on direct interaction with light to produce, to undergo photosynthesis. They don't have direct recourse to energy. So mitochondria come in great handy for these multi-layered organisms, these complex organisms that have buried structures. And they need to have some sort of internal source of energy or energy storage, sort of almost like batteries. Processes, that is, extensions that permit long-distance communication between far-flung cells in different parts of an animal's body. Explosion of new cell types, neurons, receptors that come in various varieties, including chemical, mechanical, temperature, etc. Cellular junctions, tight junctions, cells that are next-door neighbors that can send regulated signals across membranes within and between one another. So intracellular communication, action potentials, eventually movement of current across cellular membrane and eventually across great distances. When we're talking, for example, about the spinal motor neuron in a giraffe, we're talking about pretty vast distance. We're talking about at least a meter, perhaps a little bit more. That is the distance of an axon in the spinal motor system of a giraffe. Sensory cells leading to sensory organs. You just saw a little example of that from simple eye spots, light-sensitive spots of cells, to full-blown eyes. Cells and systems of cells that respond to the world and body signals across space and time. All right. Cephalization, which is sort of fundamental as well. The idea that a central clustering of neurons that actually process and record signals from the world and are capable inevitably of making up dynamic representations at some point appear, and certainly during the Cambrian, this is one major innovation. Okay, so the question I asked myself early on when I started this little intellectual adventure about 10 or 11 years ago was this: have similar properties underlying sophisticated functions and behaviors emerged in nervous systems which are radically different from those of vertebrates? And in particular, obviously, I was thinking of consciousness. And that's still rather a radical thought for many people. Octopus vision perhaps offers a clue to this question, and it certainly offers an opportunity, as I hope I demonstrate here today. So if you look at a relatively humble organism like C. elegans, Caenorhabditis elegans, 19,000 genes, give or take, a mere 302 neurons, of which we have essentially recorded and studied every one. We can now excise individually each of those neurons to see what happens. So it's an incredible test bed in neurobiology today. It's quite simple, however. To Aplysia californica, a humble marine snail. Here you see the gill withdrawal reflex, which eventually Eric Kandel and his associates used to essentially demonstrate forms of learning in this animal, and eventually LTP, long-term potentiation. If you look at the circuit diagram for the humble marine snail, it's rather interesting. This is from a very early paper. I think it was a simple Scientific American review by Kandel in 1979. It looks like a fairly simple circuit diagram, even though these animals are capable of rather complex behavior. Now, would I argue these animals are aware? I wouldn't. Some people would. And again, we'll get into that. So varieties of what I've just shown you have been identified in myriad organisms by now. And this is just one example. Long-term potentiation and its role in avoidance conditioning in octopus has been demonstrated robustly through avoidance of an electrical shock, for example. The red ball becomes associated with shock, as well as some seminal neurobiology that identified certain regions high up in the octopus brain that were associated with learning. And by the way, these particular areas, the vertical lobe and the median superior frontal lobe, were very well known to pioneers like J.Z. Young, starting probably in the 1940s and 50s when he did his investigations. And he's still the man most associated with the most seminal neurobiology of the cephalopod mollusks today. So over time, and particularly within the past 10 or 15 years, we've actually been able to identify invertebrate analogs of vertebrate hippocampus. And I'll get to why this is actually important to my case in a minute. So for example, in the mushroom body, we see some trace of something that looks sort of hippocampal-like in terms of what the function of this particular organ in insects, in particular the honeybee shown here. In the case of cephalopods, like the squid, again, the vertical lobe, associated with memory, and in particular in the octopus and squid, but the octopus especially through the wonderful experiments of J.Z. Young, who was able to demonstrate essentially that if he ablated vast portions of the vertical lobe or took it out entirely, he could really essentially disable or totally sort of remove the capacity to form long-term memory, which was rather a breakthrough, and it happened quite early on. All right, and the reason I presented that is that memory is a very important component of my case, because I claim that conscious experience is at least dependent in part on the ability to remember or to hold together a dynamic representation that is composed of multimodal or submodal properties of a scene, bind them together so that they, and then persist, have that particular representation dynamically persist in memory. So modest nervous systems, as we know, are capable of generating impressive behaviors, right? So on the top you see fighting Drosophila, fighting fruit flies. This was from Ralph Greenspan's lab about 15 years ago. And they're fighting over food. They're literally on a food dish, and they're displaying this incredibly aggressive behavior toward one another. And eventually one flips the other over, but they keep on fighting. Waggle dance of honeybees. The hunting behavior of jumping spiders, you'll see, and maybe you already saw. He jumps onto a bee from a distance and is able to kill and eat that bee. And then finally, these amazing sort of color displays of cuttlefish. Cuttlefish are capable of dramatic behaviors. This is just sort of one example. So there are these impressive suites of behavior, but really, one fundamental question is how much and what sort of a brain is required for conscious experience? And from these studies, we really haven't quite been able to settle on an answer for that. But seminally for my work, what about outside the vertebrate lineage? Okay, so exploring consciousness in far-flung species, what does this mean? Well, it means we have to start with theoretical questions. Namely, to begin with, what is consciousness? Practical questions, what brain structures and functions are necessary for consciousness? How do we study consciousness? Which animals should we study? Is the octopus a good candidate? Near and dear to my heart. Sophisticated faculties, learning and memory have been demonstrated in very sophisticated forms of learning and memory do exist in these animals, and particularly complex suites of behavior. Sophisticated but not overly complex nervous systems relative to us. We have something on the order of 86 billion neurons in our central nervous, in our brains. Octopuses have up to 500 million neurons, so it's really a fraction of the human case. But if you want to look at it this way, in their central brain, common octopus have twice as many neurons as a rat, and rats are no intellectual, or they're no slouches. We shouldn't say intellectual. Cognitively, rats are no slouches. And we have to finally make a tractable and systematic approach to this. So my approach has been to start by considering how I would map the octopus visual system, work out the neurophysiology of visual perception, and then finally come up with hammer out some sort of a provisional evolutionary hypothesis, knowing, in fact, that I have to avoid the pitfalls of parsimony, that I don't want to fall into a pan-adaptationist trap and say simply that everything that comes about or everything that we see in terms of properties, behaviors, et cetera, is necessarily bootstrapped on an adaptationist scheme. I'm sort of following Stephen Jay Gould here in a way. I'm not Gouldian in the sense that I'm not dogmatically, I'm not anti-adaptationist. I just want to be careful about my explanations. Constraints on network properties. We have to ask the question, do the same general principles apply to all complex nervous systems? All right. So here's a working definition for you. It may be a definition that many of you don't agree with, but it's the definition that I use as sort of my guiding light for the moment unless something better comes along. I think of consciousness as the stitching together or binding of many closely contemporaneous sensory threads, that is, either submodal properties of vision coming into your eyes, depth, light and shadow, all of these sorts of things, wavelength differences, distinctions, and the persistence of that bound representation in memory. And my definition of memory is rather Catholic, that is to say, rather liberal. I have a habit of using these words that I think have been lost on many people. I mean Catholic in a very secular way. A very liberal notion of what memory is. Memory, to my mind, means that the representation can stick around for a matter of 10, 20, 30 milliseconds, 50 milliseconds. If it holds together long enough for the animal to do something with it, that's good enough for me, although I know it's not good enough for many other people. So this sort of is the synopsis of that. Conscious states are bound scenes that offer content that is correlated in time, beyond that arising from segregated sensory inputs. Kind of akin, and I'm using integrated information not in the Giulio Tononi and Christoph Koch sense, more or less, more in the sense of something like the Santa Fe Institute. All right, so this view suggests that a surprising number of non-human animals may be capable of subjective experience. So the octopus is a good candidate for testing the phyletic boundaries of consciousness. I pose this as a question, but I do believe this is the case after working with them for some years now. They have sophisticated nervous systems, though less complex in gross organization than the vertebrate case. They're functionally convergent, but they show, for example, NMDA independent LTP, which is quite different from us. And they have learning and memory faculties that seem to be comparable to some mammals, at least, and certainly a number of birds. Diverse behaviors across species indicate to us that there are possible differences in neural properties that are driven by selection pressure that comes from a very, very rich and variegated environmental context. In other words, they have evolved and continue to evolve in environments that are incredibly rich temporally and spatially. Okay? Behavioral flexibility that rivals some of that of the higher vertebrates. And so let's just start with a benchmark. A benchmark in an animal, well, in the case of humans, an animal that can give us a verbal report. In the case of non-human animals, if you're clever enough, in the case of mammals, a non-verbal behavioral report. So these are some basic criteria that we can kind of hammer out for consciousness, starting with the mammals. Brain regions that function like thalamus and thalamus and cortex, excuse me. Thalamocortical and corticocortical reentrant signal that occurs therein and between these structures. So they don't have to be thalamus and cortex. They just have to act like thalamus and cortex. Okay? Dynamic neural activity, firing of neurons across the cortex that resembles what we observed during the human conscious state. The ability to make sophisticated discriminations, which would suggest a deep reciprocal connection between perception and memory. Okay, so bastardizing the Thomas Nagel quote, "What is it like to be an octopus?" Well, embodiment is also important to this picture, and octopuses present a rather strange and obscure case of this. They're really like nothing that we deal with in the way of conscience and of complex and perhaps sentient organisms generally, normally. So, all right, so this is very familiar neural architecture. I won't dwell on the structures here, but just to sort of give you a quick glance. We have names for a lot of these structures in the cephalopod mollusks, including the cuttlefish and the octopus. So these structures, many of these structures are named, but very few of them are very well characterized neurophysiologically. All right? We've started to do these kinds of things. Many people have, actually. So there have been EEG recordings in free-behaving octopuses. We did a little bit of this to test, essentially, whether we could pick up a signal that could be correlated in the octopus's brain that could be correlated with blue light, for example. And indeed, we found that correlation. It was very simple. It's a sort of proof of principle. These are important sorts of studies for identifying the mechanisms of perception, but we should probably go for a lower-hanging fruit first. So I'm going to rush through all of this just to get to the really interesting stuff. All right, so let's start with the octopus eye. A beautiful piece of convergent evolution. If you look at a cross-section of a cod eye versus a cross-section of an octopus eye, there's a lot of similarity. They have retinas. Their retinas are a lot simpler than ours. The light signal actually has to pass through layers of cells in the case of the mammalian retina, and the photoreceptors are way in back. And moreover, their axons are mounted sort of bass-ackwards, if you'll excuse the expression, and the axons actually have to turn around and pass through a hole in the center of the eye. No such issue with the octopus. The photoreceptors pass the light, get the light, and pass it directly through into the central brain. And we've started to map a little bit of this. And interestingly enough, they have a simple retina, but the structures in the central brain that first get the axons from the retina actually physically resemble the cells that we associate with the neuropile in the vertebrate retina. It looks like the processing for that signal has been offloaded into the central brain. We know that octopuses and other coleoid cephalopods have rather good spatial acuity, and you can see where they fall in this. That's rather remarkable, given who their neighbors are. Okay? And so here's just a very simple movie, and if we want to sort of start it, if you can start it kind of toward the middle there. Okay. So what you'll see is, watch the animal. Okay, that's it. Watch what happens here. Now, this animal has watched another animal learn how to get a crab out of the box. So this is no trial learning. This is essentially sort of a form of social learning. It doesn't happen with every octopus, but it happens with some. So eventually, you're going to see him approach the box. Here he goes. And he's going to go over to the door that he happens to know from watching the previous octopus work with the box will work and get him to the crab. He opens it up. Takes him a little while, and then he goes in and he gets the crab. I'll just wait for that to happen, and I'm going to quickly switch. There he goes. He's in, and he's going to get the crab rather quickly. But again, this was not trial and error. This was no trial learning. He just simply watched another octopus doing the same thing and then repeated it himself. Okay, this was done by Graziano Fioritto at his lab. So what we want to do is we want to introduce a psychophysical approach to this problem of perhaps studying awareness in octopuses or probing for awareness. So psychophysical approach allows us to do all these things. We can monitor behavior for changes that indicate perceptual and integrative functions at work. We can identify neural correlates of perception and integration. We can investigate or monitor possible conscious states. And these are some of the salient stimuli that we pick out for the octopus. Of course, we want to start with salient stimuli because they are most meaningful to the animal, and we can do kinds of conditioning experiments that condition them to things that aren't in their natural environment, like red balls versus white balls, etc. Okay, all right. So we have developed a video presentation system, which what you'll see here when the movie starts, if you can start the movie for me, you will see an animal whose den is on the right of this brick. The camera's hidden in the brick because if it wasn't, the octopus would take the camera apart. So it's hidden in a brick very surreptitiously. You'll see the animal approaching the screen. What you'll see very difficult to resolve. There's a crab going across the video. He goes for it. He hits the wall. And then watch what he does following this, which is rather interesting. He stands back. He uses one eye to get a glimpse at where that crab seems to be, and then he tries to go for it again. Okay. All right. And then we sort of simply studied the visual system with sort of fast versus slower sequences of a sort of a movie that we slow down to the point where it's essentially single images. We want to see how fast octopus vision was. So you can see they respond very quickly. This is the screen on one side the animal's responding to. This is what the animal is seeing. And he's trying to get that crab. I'm going to go through, again, rather quickly. We can go all the way down. He'll still respond pretty robustly. There's a little bit of a latency. I won't stick around for this because I know we were running very short on time. But you'll see we can go really far down. And this relates to what I talked about, a Catholic definition for memory, essentially something that holds together for a certain period of time. This is very relevant to that. And you see that if we go down to 4 hertz, watch what happens. There's sort of motion, but it's like Charlie Chaplin-like. Watch what the animal does. The animal will come to the center, toward the center of the tank, very cautiously. It'll change 1/2 of its body's coloration in relation to what it sees. We don't know what that means. It's some ambiguity. And then it kind of goes and tries to attack. And then finally, when we get to 0.5 hertz, it's literally a series of still images. And the octopus just sort of sits there flummoxed. He doesn't know what to make of that. Okay? All right. So finally, visual navigation. It's another way to sort of look into the prospect for memory. In this case, spatial memory. And again, I think memory is important to make my case. So you're seeing a Barnes maze from above. And these are a bunch of fake egresses to the water tank below. They're fake. He can't get to the water from these things. But there's one real one. You just saw him disappear into it. So let me go through this hypothesis really quickly, and then I'm going to rush off the stage. So here's the idea. Animal with focusing eyes, that is, eyes with lenses whose distance could be varied between the lens itself and the retina in a single compartment, were essentially more complex and developed more flexible behaviors than other members of their phyla. Distance vision via focusing camera eyes gave them more time to plan for and act on far-off salient events or objects within a detailed visual scene. Distance vision also evolved in tandem with neural circuitry for monitoring and prediction. What I'm going to ask you is a simple question. What is a complex eye that is capable of distance vision and distance from close by? What is it there for if it doesn't have the neural circuitry behind it to process the complexity of a distance visual scene? Moreover, that sets the stage for inhibitory circuits so that the animal doesn't immediately respond. We know for a fact this happens in the case of octopuses. They can see something from afar. They don't reflexively respond and attack it. If it's a predator like a moray eel, they'll sit and they'll simply see what the moray eel does. If it's a prey species like a fish that the octopus eats, it will do sort of the same thing. So it's sort of monitoring, which is intriguing. And that is an ability that is afforded by distance vision. So it's a new kind of a memory substrate that's coming about. Distance vision allowed the generation of more detailed visual scenes, comprising submodal properties, textures, contours, intensities, colors. Mapping these properties entailed the development of a specialized neural architecture and the means of integrating all of these submodal properties. And that led the way to higher order dynamic mapping. Okay, finally, integration of a unitary visual scene, new kinds of memory, and the emergence of reentrant circuits connecting visual perception and visual memory. That's the part that is cortex communicating back and forth with thalamus. But in the case of the octopus, of course, we don't know analogically what those cortex-like or thalamic-like structures actually are. Okay, and this could have yielded some form, I believe, of incipient sensory consciousness. Thanks. Thank you very much.
Thank you very much, and thank you to all of our speakers. I'd like to invite them up to the stage. And while they're coming up, just an announcement. John McKenzie has left a bag, and they're holding it in the back. So our speakers will come up. I think microphones, or, oh, they've got theirs. All right, and questions from the audience. And please try to keep them brief and focused. Sir.
I have a question to Eva. Thanks for the talk. If you assume that minimal consciousness is a qualitative definition and evolution is a gradualist approach, how can you bring these together? And wouldn't it be make much more sense to have a gradualist definition of consciousness, like, for example, also in ontogeny, where we see a child moving towards consciousness rather than having this strict definition of minimal consciousness?
Yes.
Let's see. No, I don't think you should. It should be. Hello? Yep.
Okay, thank you very much for the question. First of all, I want to say that what we are suggesting with this unlimited associative learning, it is a positive marker of consciousness. It tells you which animal we can be quite sure of, reasonably sure of, has consciousness. It doesn't tell us exactly which doesn't. There is a very big gray area. When you're looking at the evolution of one of the things we did was to follow the evolution of learning from the very beginning, from reflex, from the modulations of reflexes through habituation and sensitization, through limited associative learning, and of course there is gradualism. There is a gradual change. We are not sure. We want to put the line somewhere. Now, the point where we're putting the line is where we're quite sure that we can defend a position. Before that, the criteria are too fuzzy for us to make an actual decision. So it is only a positive marker, not a negative marker, and there is a big gray area before that. And whether or not you assign consciousness to an animal that is in this gray area very much depends on how you think about consciousness, on your theory of consciousness. Whereas we think that once we pass this threshold, we can say something with more certainty. In the same way as life, there is a particular organization of chemical networks where we can say, yes, once this organization exists, we can say this entity is alive. There is another, at the other pole, there are networks that we say, no, they're not, that's for sure not indicative of a living entity. In between, it very much depends on your theory. Now, as to the young child. The young child has the enabling system for unlimited associative learning. Of course, it cannot learn in this way. But it is so. But it is the enabling system that is conscious, not the system of associative learning per se. So, in the same way that if you take out the nucleus from a cell, for example, a red blood cell, the red blood cell will continue to live for 120 days, quite a long time, in spite of the fact that the unlimited inheritance system of in the nucleus, the DNA in the nucleus, is not there. Why? Because it has enough around it. It will not live forever, right? But it will live for 120 days. We are saying that if an animal would lose during evolution its ability for associative learning, then it will also lose consciousness in evolution, not in ontogeny.
Mm-hmm. Thank you. Question over here.
Yes, thank you very much for some brilliant talks. I'm just curious and reflecting on our definition of consciousness and that the particle field sort of orientation. It's like, as we're looking at specific animals, the octopus or other animals, what about the idea of the field and consciousness in such organisms like ants or these other kinds of species that don't seem to have individuated in terms of the particle, but as a field, certainly in terms of the social consciousness and the function at those other levels, there's a different perspective of consciousness that seems to be operating in a collective way differently than what we're assigning to our particulate unique association with consciousness.
Oh boy, I'm kind of on the spot. Yeah, unfortunately, I haven't given a whole lot of thought to, so-called eusocial animals, such as ants, where there does seem to be sort of collective behavior and a very sort of an organization of collective behavior. But I will say that I'm rather skeptical of the notion of something like conscious awareness emerging in such a social system collectively, simply because I think the temporal dynamics are sort of wrong. I mean, I think that it's too slow in a certain sense. Even though the behavior is quite adaptive and the animals do stuff, in short enough order to sort of save themselves, to keep themselves alive, collectively and even individually, I would say we're not talking about the same thing as sort of the temporal dynamics of an individual complex brain doing what it does in a matter of milliseconds. And I think in a sense, it's very hard to imagine some sort of representation in that collectively organized social structure versus a dynamic representation within a single brain.
Well, I agree about that. And we are, at cross purposes, about the way we use consciousness. It's, I think Eva, and David to the large extent, is defining consciousness as a cognitive faculty, which helps us with decision-making, pattern formation, integrating information, and so on. An immensely important thing to do in a sophisticated mind. It was a very good trick when nature hit on it to develop a global workspace. And it, not surprising, we find something like that reduplicated in different animals and with different brains. But also, I think sometimes it could well be in social systems as well. They might well benefit from a similar way of managing information. None of that would make any of these systems phenomenally conscious. There's no reason to think it would be like anything to be a system which has such a global workspace chugging away and solving all these problems. For that, I think there had to be a discrete new development in evolution, and that, I think, is pretty much all or none. Joshua Rock gave a wonderful talk yesterday about consciousness as either being on or off. And I think when we're talking about phenomenal consciousness, that's absolutely right. But if we're talking about the consciousness Eva is describing, that certainly could emerge by stages. You just get closer and closer to the ideal system of unlimited associative learning and all the other things which follow from that.
Just one thing, that the social system is far less autonomous than the individual animal that consists on it. And in a way, the social system is reflected in the brains of the social animal. So there isn't a brain of the collective. There is a brain of individual animals that reflect a collective dynamics.
Thank you.
I think your idea of definitions.
I'm sorry,
of
we're going to have to
consciousness.
move on. We have a lot of individuals here who want to ask questions.
Thank you. This is a question for Dr. Edelman.
Yeah.
I'd like to explore the connection between long-distance vision and consciousness. Suppose you were to discover a form of blind squid. Maybe they're trapped in caves and so they've lost their vision. What would you predict about their consciousness?
Interesting question, and one of the caveats that I did not include in my talk, which I studiously always manage to do normally, is the idea that what I was arguing for is the notion that vision is an early bootstrap for conscious processing in brains, but vision disappearing in brains developmentally or evolutionarily does not mean that the substrate that initially appeared alongside early distance vision disappears as well. So in other words, I would never make the claim that moles, or certain moles, by virtue of the fact that they're blind, are not capable of conscious experience. Because as we do know, again, through experiments and development, but just looking across animals comparatively, in fact, it's certainly possible for brain circuits to be co-opted by other senses. There have been myriad experiments done in which this is the case. David Edelman has pondered this idea, among other people. But it's an interesting question. So in the case of a squid, not an octopus, it's interesting. They're a bit more primitive in terms of when they appear and what they're able to do. In the case of a squid that's blind in a cave, it sort of depends on where that squid came from evolutionarily, right? So if that squid has an evolutionary history that comes from a sighted squid, it might be easy to imagine that the brain structures were co-opted and other sensoria sort of started to fill the void of spatiotemporal representation of some sort, even if it was not quite as good or as fast as vision. I hope that helps.
Thank you very much.
Sure.
Thank you. Sir?
Yes. let's say we judge the success of a discipline on the basis of the extent of its explanatory power, even to the point of cross-disciplining, and drawing on a quote from the last speaker, everything in the future is a wave, everything in the past is a particle. Suppose we have this very advanced creature observing, call him a quantum physicist, and discovering that a particle's existence comes in through that sentient observation and doesn't have the past is potential. Now, could that research eventually lead to an undermining of evolutionary theory that is based on a chronological past? Or am I crossing disciplines too much? Because this whole conference and 20 years of it is about who defines what consciousness is. But my question is, to what extent can your explanatory power delve into this type of sentient observation that denies or questions? I'm quoting Wheeler, physicist Wheeler, when asked, does the Big Bang begin with observation? Is somehow the Big Bang now? And he says, in one day we will discover, if anything learned from quantum physics, that the past and future are in some sense transcended. And that, yes, the Big Bang in some sense will be considered now. So what answer might you have to that kind of threat?
Gosh, I think I have to maintain a sort of a variant of Colin McGinn's idea of Mysterianism, only into the quantum world. I have to extend this notion of Mysterian, of a Mysterian view. That is, I'm not equipped to sort of understand it, so I don't think I can provide a satisfactory answer for you.
I also can't, but I will say one thing. As a scientist, I think evolutionary biology is the most powerful theory in biology that we have. If there is a theory, whether it is Chomskyan linguistics or some interpretations, as I understand it, of quantum theory, because quantum theory, as I understood it in this conference, has many interpretations, that do not pass the bottleneck of evolutionary theory, then these theories have a very big problem.
Yes, I think Eva's taking the same line I would about it. People like Tom Nagel, for example, believe that somehow the universe is teleonomic. We are being controlled by some future destiny which the cosmos is working towards. And of course, Wheeler's idea of the eye at the end of the universe also would involve that idea of things being organized retrospectively. In that case, why would evolutionary theory be such an astonishingly successful explanation of how the content has come into the design and arrangement of animals' lives built from the ground up? If something's pulling us forward to them, then we wouldn't expect to need these theories. And in fact, doing biology would become extremely difficult. W.D. Hamilton, a great evolutionary geneticist, of course, did play with the idea. He thought we were puppets of some higher power, and that he said every now and again that the puppet doesn't quite like the evolutionary project it's set up, so it sticks its finger in and changes it a bit. And he says that's what the religious people call miracles. I'm glad to say it was mostly tongue-in-cheek, though, because his whole enterprise would have been a disaster if he really believed that.
Thank you. And we're only going to have time for the questioners who are currently at the mic. Sir.
First, I'd like to thank all three for stimulating talks. First question for Eva has to do with the immune system, meaning if I take the 7 conditions for minimal consciousness, it seems every one of them is satisfied by the immune system, except perhaps one that you could add, make it an 8th one, and that has to do with the counterfactual emulation, what Andy Clark calls counterfactual emulation, that actually engages the self-model so that you kind of project yourself into imaginary situations. Which brings us to the octopus, which definitely seems to do that. And my question then would be whether it involves this a typical signature of gamma, theta, cross-frequency phase locking, and whether you're looking for that. Thank you.
Do you hear me? I think that if you want to, first of all, I want to say that it's very interesting that the immune system and the nervous system co-evolved. And there are theories about the origin of neurons that are that suggest that it started. There are several theories, so it's not the only theory in the market of theories. But one of the theories about the evolution of the origin of the neuron is that it evolved from a cell that had repair functions, from signaling cell that was involved in repair functions. This is the theory of Leonid Moroz. And some other people, but he developed it particularly well. Now, as to your question about so that's just an interesting and I think very important observation, because when we're thinking about the evolution of real animals and about the evolution of the nervous system and a certain type of nervous system, the way that it didn't evolve in itself, it evolved with a body. It is another interesting fact that all animals with the neurons, with the nervous systems, with one exception, have muscles. And the one exception is Cnidaria, which is parasitic. So it lost its muscles, but all others have muscles. But anyway, if you are looking at the list of the 7 characteristics that I gave you, you can metaphorically, if you use metaphorical, you can say that it can fit a lot of things, but I don't think it can. We tried it on the immune system, and for us, it didn't work. Okay.
Thank you. And I'm sorry, to be clear about my earlier comment, anybody who's in line can remain in line. Sir.
Okay, thank you very much. I have a very broad question. It seems to me that in order to be effective, an evolutionary approach to consciousness, one must hold the assumption that consciousness has a functional role, because otherwise it could not have been selected through natural selection. And that would lead also to another consideration, that if that was the case, it might be possible in principle to predict the appearance of consciousness during evolution, because like flight, like movement, like other basic feature for survival, it should be a necessary functional aspect. And I'm not completely sure that we can provide. Maybe we will be able, but right now I'm not completely sure that we can do that we can make that assumption that consciousness is a functional, can be translated into any kind of functionally effective element.
Well, of course, we all have our own ideas about that. I put forward what I think is a functional role for phenomenal consciousness, which in its most elementary form is to boost the sense of the self and make it a useful focus for our behavior. On the question of predicting when consciousness would come in, I think it's a very interesting question. The story I outlined is actually a story of a chapter of accidents, things we could never expected, the fortuitous link-ups and so on, which occurred in the brain because of the previous history that they'd arrived at. And so I think that it's extraordinarily unlikely that if you ran the evolutionary record over again, you would get phenomenal consciousness emerging. I think it was an extraordinary piece of luck that it's happened. Going further than that, it makes me think that consciousness as we know it among human beings is probably unique in the universe. I think it may exist in some of our relatives in this world, but I doubt very much it exists anywhere else outside. And I was struck by Frank Borman, the Apollo astronaut, who looking at the Earth remarked that what was so extraordinary was that the Earth seemed to be the only entity in the universe that had any color. Well, he may not be right about that, but I think it's probably the only entity in the universe where anyone experiences color as we do.
I think that the function question may be misleading. I don't think consciousness has a function. I think consciousness has a telos, like life. You will not ask, what is the function of life? You will ask about the functions of those processes and of those factors that make life possible, and they have functions. And their function is to lead to the maintenance of the system in this case. So in this case, the telos of life is self-maintenance, both in ontogeny and over historical time. In the same way, I think that it is not helpful to think about the function of consciousness. I think it is very helpful to think about the processes that constitute consciousness, such as unlimited associative learning, such as many other very, very interesting processes. And they have very great function. The function of unlimited associative learning is incredible. It is a game changer in evolutionary biology, because you can adapt ontogenetically, where before that, you had to adapt phylogenetically, or mainly phylogenetically. So I think that asking the question about the function of consciousness is a misleading question. We should reframe the way that we think about it.
I'll just add one really quick thing, which is that, and I didn't make my case strongly enough and as explicitly as I could have in my talk, but the point, at least I was implicitly trying to make, was there are certain building blocks. There are requisite faculties that, in fact, we know evolved and do have quite an adaptive function, among which are memory and certain aspects of sort of immediate perception, whether it's vision or hearing or tactile. But memory certainly evolved, and it's been elaborated, and it has an evolutionary history, and you can certainly make a case that it is adaptive. As to consciousness, I guess I'll leave that open. I have my own ideas, but that's for another time, and perhaps we can discuss that during a break.
So we have 4 questions in 10 minutes, so let's have very focused questions and answers. Sir.
This is a question to Eva. You have developed a set of criteria for a certain level of consciousness, and you have explained to us that probably around the Cambrian time, the creatures were able to come to this level. I'm interested to understand the connection to what Roger Penrose was saying. So he made a very strong point about computationability. In the short time, I was not able to understand everything you were showing, but at first sight, it seemed to me that all criteria would be computational. So would you agree with that today's computer programs, like robots whatsoever, would fulfill the criteria, or put it another way, on the same level as Cambrian creatures?
I don't think that today robots or simulations and programs fulfill what is needed to create something like a sentient robot. I am not sure about, you asked me about Penrose, I wish I understood the theory better. But it is the only theory that I have come across from this quantum physics realm, where it takes into consideration some biological aspects, and I think this is a very welcome thing. But going back to your question, I think that without value systems and the hierarchy of value systems, I don't think, and not specific value systems, not how to win a Go game, right? But how to self-maintain in a changing world, how to evaluate all kinds of things at the systemic level in the way that animals do, how to respond to social cultural symbolic values. We will not have and to build it gradually during the ontogeny of the machine, probably, although I don't know what shortcuts are necessary. But without this value system, nothing like sentience, in my opinion, will emerge from today's programs. I'm not coming from artificial intelligence, so my understanding of these things is not very great, but from what I have read, this is my conclusion.
Thank you. In the back.
Okay, this question goes to Nicholas, because you mentioned it, but anyone can comment. So can you clarify the relation between self-representation in a system and consciousness? Why can't a neural network have information about itself without a self that is conscious?
I think it could. I don't think self-representation as such is a mark of phenomenal consciousness at any rate. And in fact, many artificial intelligence programs now are building in a self-model into the system, which turns out to be a very useful way of actually economizing on the kinds of behaviors which are thought to be relevant to the next step and so on. I think, as I just said before, I think that level of consciousness is a very good trick, just for helping to generate adaptive behavior in the world. Phenomenal consciousness, I think, is kind of selfhood at a very different level. And that, I think, isn't by no means a necessary consequence of being a self, any more than it's a necessary consequence of having sensations. I think sensations need not have the phenomenal component, but in us, at least, they did, and probably in some of our relatives. And the question becomes, okay, what was the added benefit? What was the payoff of developing this next dimension of experience? And that's why, as you'll see, I part company with my colleagues here about thinking at what level we should address the question of consciousness.
And finally, you, sir.
This is a question to David. Do you think, quick question, do you think your octopus is self-aware?
Yeah. No, I'm not sure. I don't mean no. I mean, I am really not sure. I have to remain agnostic about that. One of the things that I should also say about what I talked about is that I was very much presenting a notion of consciousness that is a sort of a primary form, and that is an awareness of a scene in the possible absence of a self. So I make the same distinction that my late father made between some sort of primary representational schema and some sort of schema in which embedded there is a self. So, I'm purposely, I'm not trying to evade an answer to your question, but I've purposely evaded this issue in my own research. I've just avoided that altogether. And if you notice, if you'll go back to the definition that I offered for consciousness, it's very elemental. And it doesn't include, nor does it necessitate, the notion of a self, merely the awareness of a scene in mind.
Thanks.
Wonderful. Well, again, thank you to our three speakers, and thank you to the engaged audience for a wonderful panel.